Good morning, grade 11 physics students. It's Thursday, April the 23rd today, and we are well into our online learning system here, and I hope it's going well for you. Yesterday on Wednesday, the test for the last unit was posted. Hopefully you've been able to get at that test, print it off, write it, and you'll be getting it back to me in the very near future. And hopefully it's gone well. If you have any questions, make sure you ask. Send me an email, phone me, whatever it takes, get a hold of me, and make sure that you ask those questions. All right, today we're starting a new unit on waves, as you can see behind me. And but before we get to that, let me encourage you with a verse of the day today. Over the last little while, I've been reading through Psalms. The devotional that I'm going through is going through some various Psalms. And again, today's Psalm is out of Psalm 33. In Psalm 33, again, there's a but statement. And again, these but statements are truths that we can count on. And so here is today's Psalm 33, verses 16 to 18, where it says, "No king is saved by the size of his army. No warrior escapes by his great strength. A horse is a vain hope for deliverance. Despite all its great strength, it cannot save. But the eyes of the Lord are on those who fear him, on those whose hope is in his unfailing love." And so it's a reminder to not put our trust in the things of the world, in the horses or in the armies or in science or whatever it might be. Those are all good things, and they're good things to have, but our ultimate hope and our ultimate trust has to be in our Lord Jesus Christ, and our hope should be in him and him alone. So let's move on to waves. Now on the board I'm going to talk about a few things, but it is really a summary of some pages in your textbook. And your assignment is going to include reading those pages. If you have your textbook handy, you could pause the video at this point and grab your textbook and open it up to page 381, as what we're going to cover on the board behind me is a summary of what it talks about in those pages. And if you have your textbook with you, it will save you from scanning or reading those pages later on as you prep for the few questions that you'll have to do at the end of this. So we're talking about waves, and the first thing you have to ask yourself is, what is a wave? And waves are one of those things that are hard to define, because we've all seen waves, and we all have a concept of what a wave looks like in our head, but what actually is it? And we all know too that waves take many different forms, right? We have water waves, we have sound waves, light waves, we have all kinds of waves. But the definition would then seem to be nebulous, in fact, that there's so many different waves, how can we define it with one definitive statement? Well, we can, because all waves are simply, and this is important, this is what you should take note of, a wave is a disturbance in a medium that transfers energy. So it's that simple. A wave is a disturbance in a medium, and the medium can be air, the medium can be water, the medium can be a spring. I've got a spring right here. This could be a medium where a wave travels through it. It could be anything. And so it's a disturbance, a pulse, something, a disturbance that causes energy to move from one place to another place. That is what a wave is. And waves have certain components. And the first two things we want to talk about are things that we've seen before and heard of before. We did a pendulum experiment earlier on in this course where we talked about things like frequency and period. And I just want to remind you of what those are. So frequency, which is a symbol is F, is the cycles per time. So when we did our pendulum experiment, we had a pendulum that was going back and forth, and a cycle was the time it took to go from one side to the other. That was a cycle, to travel from here to here, and we measured how long that took. And so frequency is the number of cycles in a particular amount of time. Okay, we're going to go cycles per second. Seconds is our unit. And a cycle per second is considered a hertz. Now again, you've heard the unit hertz many times. Anytime you listen to the radio stations are measured in megahertz. And so we've heard of hertz for frequency. And so it's the number of cycles over time. Period is the inverse of that. Period, which is the symbol is T, and the symbol is T because the period is the time for one cycle. So it's time over cycles. And the unit for that is, of course, seconds. All right, so these are inverses of one another, which means that frequency equals 1 over the period, or period equals 1 over frequency. Right? That's the crux of an inverse statement, a reciprocal statement, where we have this. All right, so that's the first thing, because waves typically are periodic, which means that there's multiple waves traveling through a system, multiple disturbances traveling through a medium. And they're periodic, which means we have cycles. Each wave crest can be a cycle, and that cycle, a number of those wave crests will pass a point in a particular amount of time, giving waves a frequency, and therefore then a period as well. Whew, Mr. Peters just gave me a heart attack. He's rattling my door. It's okay, I did it to him earlier. I don't know if he was doing it for your class or not, but I did the same thing to him. All right. On the board here, I have a diagram. And again, these pieces that I've got in the diagram of a wave are explained in detail in your textbook. I'm going to go through them anyway and do it. So here we have a typical wave, okay, a wave pattern. In the middle, we have a line of equilibrium. If there was no wave, everything would be flat along that middle line. But we've created a disturbance. We've created a wave that is now traveling through this. And this can be water, this can be a spring, this can be anything. Okay? Not anything, shouldn't say anything, sorry, can't be anything. It's a particular type of wave. All right, waves have parts that are above this middle line. Parts that are above it are called crests. Okay, it's the wave crest. Again, a term you're all familiar with, crest, the crest of a wave. All right, the parts that are below the middle line are called troughs. So we have crests that are above, we have troughs that are below. Okay, so we've got crest, trough, crest, and so forth. All right. The distance between the middle line and the highest point is called the amplitude of the wave. Okay, now amplitude is a measure of how much energy is being transferred. The larger the amplitude, the more energy is being transferred. Okay, amplitude does not have to do with things like velocity or frequency or even the wavelength of a wave. It is simply the larger the amplitude, the more energy is being transferred. So it's the difference, the distance between the middle point and the highest point. It's also the distance from the middle point to the lowest point. They should be the same. So you see me got here, I've got labeled amplitude, amplitude, amplitude. They should all be the same. All right, so we've got crests above, troughs below, amplitudes, the distance between them. Now, the other part of a wave is called the wavelength, and the wavelength is simply the distance between successive waves. So here, I've got it labeled as the wavelength is the distance from this crest to this crest. Okay? It could be the distance from this trough to this trough, be the same distance. Okay? So we just need it as one. It's measured in meters, as always, things are always measured in meters. And the symbol is this Greek letter lambda. It's sort of an upside down, backwards Y. It's the Greek letter lambda, and it's the symbol we use for wavelength. All right, so those are the main parts of a wave. We have its crests, troughs, amplitude, wavelength. All periodic waves will have a frequency and a period, and from that we can answer questions. There are two different main types of waves. One is called a longitudinal wave, and one is called a transverse wave. And again, I'm going to get you to do some reading in your textbook, but what I've pictured here is called a transverse wave. Transverse wave is a wave in which the direction of the wave, if this was a wave traveling through this pole, through this medium, it would be traveling in this direction. So the wave is traveling left to right while the pulse is moving up and down. The disturbance is up and down, right? Because this was our equilibrium, we have an up line. So a transverse wave is a wave in which the disturbance is perpendicular to the motion of the wave, all right? And the second type of wave is called a longitudinal wave, or a longitudinal wave, and it is a wave in which the motion of the wave and the disturbance are parallel to one another. And I'm going to get you to read about that in your textbook, and in the next lesson I will give you a little demonstration. I'll try to show you what that looks like in a spring. All right, and again, there's some nice pictures in your diagram of it. And if that works, great, but I will do a demonstration. I'll try to do a demonstration in our next video. All right, when we talk about speed of a wave, the speed of the wave, if we just have a single pulse, it's our normal velocity formula. Velocity equals distance over time, which is our normal kinematics formula. If we just have a single wave that's moving along, it's going to travel a certain distance in a certain amount of time. That will be its velocity. If we have a periodic wave where we have multiple waves being created over and over and over again, then the formula just changes slightly. It changes to frequency times wavelength. All right, because now we don't also have a distance, but the distance between successive waves is the wavelength, right? And so that still is meters and meters. The frequency now is the cycles per time. So this is still 1/seconds, right? So the seconds is still in the denominator where the time is. The meters is still in the numerator, and we still get a meters per second thing, unit coming out of frequency times wavelength. All right, so if we have a single pulse, we're just going to use distance over time. If we have a periodic wave, we're going to use frequency and wavelength. Again, when you read questions, when you do questions, you'll be able to see which formula you need to use based on the information given in the question. And I think that's all I want to cover today. I think that's where we're going to stop. What I want you to do is, again, look on Connect. There will be an assignment there, a reading out of your textbook that will, again, summarize some of the stuff that I've said on the board, as well as show you a simple example of given some information, finding speed, finding wavelength, finding period. So I want you to go through that example, and then there are a few questions for you to do on page 386 of your textbook. And so that's it for today. Hopefully that makes some sense. As we get into waves, you'll see that waves are not that difficult of a concept. They follow some pretty basic rules, and there's something that we're familiar with because we deal with waves every day, right? Sound is a wave, and we deal with sound every single day. Light can be a wave, and we deal with light all the time as well. And so we see waves around us all the time, and we have some familiarity with that. So that's it. Hope you have a great day. Read the textbook, do the questions, and we'll see you tomorrow.